When we start talking about black holes, a lot of people have a misconception about them. They get this idea that, okay, black holes have this huge amount of gravity, so if you go anywhere near a black hole, it's just going to suck you straight up. They think, okay, if there is this huge black hole at the center of the Milky Way galaxy, which there is, then someday we're going to get sucked into that black hole, and that's going to be dangerous for us. Or what if, just imagine somehow that the sun turned into a black hole? It's not going to, but let's pretend it did. Well, we would be in a heck of a lot of trouble then, not just because the sun would be gone, but we would get sucked into the black hole. This is not correct. None of this stuff is going to happen. There is a huge black hole in the center of the Milky Way. It's a gigantic one, and we are never going to get sucked into it. You can imagine a black hole. Let's say there was some sort of rogue black hole wandering the galaxy, which there are some, and imagine that it came into our solar system. We would not get sucked into it unless it was aiming right at us, which isn't very likely. It would be dangerous, it would cause issues, but we wouldn't get sucked in. The question that we're going to be talking about in this lecture is, how close can you get to a black hole and not be sucked in? So this question leads us to talk about something that's called the event horizon, and it leads us to talk about a distance called the Schwarzschild radius. These are really kind of two names for the same thing. Basically, the event horizon is the exact distance from a black hole where the escape velocity is equal to the speed of light. So that's the distance where if you go inside it, nothing can escape from it because nothing can travel faster than the speed of light. Remember that the escape velocity depends on the distance you are from something, the radius of the object. So this is defining a radius that is kind of the point of no return. If you go inside the event horizon, then you're not coming out because you can't travel faster than the speed of light. So this is an important thing to talk about. Why is it called the event horizon? Well, the point is that any events that take place inside the event horizon, now what those kind of events might be, who knows, but events that take place inside the event horizon, we're never going to observe because the event horizon is that distance where no information can ever get out from there. Even a signal traveling at the speed of light, like the radio signal from your crazy friend that we talked about in the last lecture, that can't get out from the event horizon. The event horizon is the point of no return. That's the point where you would define yourself as being irretrievably sucked in to the black hole. So if I want to figure out exactly what that distance is, this is going to come from something called the Schwarzschild radius. Schwarzschild radius is basically the same thing as the event horizon. It just puts numbers on things. And it's named for a guy named Karl Schwarzschild, who was the first person who calculated it. And it's a really simple thing to come up with. You take the escape velocity formula, plug in the speed of light, c, for the escape velocity, and then you solve for r, and you come up with an equation that looks like this, which is not too bad. That's a pretty straightforward equation. We could easily plug in numbers and calculate it. There's an interesting little trick that somebody once discovered about the numbers in this. There's sort of a shortcut formula for this that makes our lives a lot easier and lets you do some really easy estimations of the Schwarzschild radius. Basically, if you plug in g, which is a constant, and c, which is a constant, and if you put the mass in solar masses, like instead of in kilograms, you take this, take the mass and convert it into how many times the mass of the sun it is, then you can calculate a Schwarzschild radius just by multiplying that mass times 3, and that'll give you an answer in kilometers. So just for the sake of argument, let's pretend that due to some crazy alien who is evil and wants to destroy us, let's say he magically turned the sun into a black hole. Well, the sun's mass in solar mass is how many times the mass of the sun is. Well, that's just 1. So if the sun became a black hole, the Schwarzschild radius of that black hole would only be 3 times 1, 3 kilometers. A black hole is very, very small. If you think about the most massive stars out there, the really, really big ones, which those will become black holes, they have a mass of about 100 times the mass of the sun. So let's say that gets turned into a black hole, which it will. Well, in that case, 3 times 100 is 300. The Schwarzschild radius of that black hole would only be 300 kilometers. That fits between Houston and San Antonio. That is not very big. You have to get ridiculously close to a black hole in order to get sucked in. What about this one in the center of the Milky Way? Well, the one in the center of the Milky Way is a lot bigger. It has a mass 4 million times the mass of the sun. Well, okay, plug that in. 4 million times 3 is 12 million. 12 million kilometers is pretty big, but it's nowhere even near the distance from the Earth to the sun. So we would have to get ridiculously close to that to get sucked in, closer than the sun is to the Earth. And so we're not likely to get sucked into that black hole anytime soon. We're 30,000 light years away from that. So not going to happen. If people ask you, are we going to get sucked into a black hole? Chances are no. Even if a rogue black hole suddenly came into the solar system, we would not get sucked into it unless it was aiming right at us so that we could get inside that little bitty Schwarzschild radius. Black holes are small. They have huge mass, huge gravity, but their radius is small. Now let's just do a couple more examples. Let's go extreme. Well, okay, let's think about the biggest black holes in the universe. These are called supermassive black holes, and we think that these exist in the centers of pretty much all big galaxies. So we're just going to figure out the Schwarzschild radius of a million mass one and a 1 billion solar mass one, which 1 billion is not quite the biggest you could get. It's the biggest that we've found so far is about 10 billion. That's a real recent result. We'll find the Schwarzschild radius of those and see if we're going to get sucked in. So for the million solar mass one, I'll just pause for a second. Well, in that case, we'll use our shortcut formula, R equals 3m. And for the million solar mass one, well, just multiply times 3. R equals 3 times a million, you get 3 million kilometers. Again, that's not even the distance from the Earth to the sun. That's pretty small. Let's take the billion solar mass one. That's a lot bigger. Well, okay, let's multiply it. 3 times a billion is 3 billion kilometers. Now, that's pretty big. That thing, if you stuck it down where the sun is, we'd be inside it. In fact, though, if you stuck that down where the sun is, Pluto would not be inside it. So it would get most of the solar system, but not even Pluto. And if you go 10 times bigger than that, it turns out, so the biggest one that we've ever discovered, okay, 30 billion kilometers. Well, that's pretty big, but it's not even a light year. So black holes are not likely to suck things in. Yes, they do suck things in. Yes, it happens. But you have to be ridiculously close to them to get sucked in. So if anybody ever asks you, because, hey, you took astronomy, are we ever going to get sucked into a black hole? Answer is probably not.